Let's look at question number 3. So the first part is we have two matrices A and B for which the product AB is defined, and if columns of B are linearly independent, then columns of AB must be linearly independent. So that's what we have to show. Okay, so start from here. Okay, so what does it mean for some matrix's column to be independent? So a matrix has independent columns if for mx equals to 0, there exists x not equals to 0. Okay, so if this condition is satisfied, it means that columns of the matrix M are linearly independent. Okay, so that is the condition. So now we are given that the matrix B has linearly independent columns. So A times B, this matrix we have to show as having independent columns. It means that there exists some x vector such that AB times x is equals to 0 for x not equals to 0. So there exists x not equals to 0. So there exists x not equals to 0 such that this thing is true. Now, given that B has linearly independent columns, it implies that there exists x vector not equals to 0 such that Bx is equals to 0. This implies A times Bx will also be 0, which implies AB times x will also be 0, and this is the x that I have been looking for to show that AB has linearly independent columns. So now my job is done. So what this proves is that the matrix AB has linearly independent columns. Okay, so that takes care of first part. Now let's look at the second part. So in the second part we want some EI. So we're saying that EI denotes the column vector with 3 elements. Basically what we have is that the E1 vector is 1 0 0, E2 vector is 0 1 0, and E3 vector is 0 0 1. So that is what we have been told. Now he's given us a transformation, the L, such that L of E1 is equals to 1 0 0, which is E1. L of E2 is 0 1 0, and L of E3 is 0 0 1. Okay, so that's how it is given to us. Oh no, sorry. L of E2 is E1 plus E2, so there is 1 1 0, and this is E2 plus E3, so this is 0 1 1. Okay. Now what we have to show is that L maps R3 to R3, R3 onto R3. Basically, all the codomain or the range of this function L must be complete R3. That is what we have to prove. Okay. So let this thing be equal to F1. This thing be equal to F1, this thing be equal to F2, and this thing be equal to F3. Okay. Now what we can show that for an arbitrary point in R3, arbitrary point, let me call it Y belonging to R3, there exists x belonging to R3 such that L of x is equals to y. Okay, so I'll start with some random arbitrary point, and I can show that for this arbitrary point there is a pre-image. ठीक है. सो कोई भी फंक्शन मेरा क्या कर रहा है, कोई दिस फंक्शन L what is doing it's taking points from R3 and it's mapping it into R3, right? So what I'm saying is take any point here y and show that for this y there exists some x such that L of x is equals to y. So when I do that for any arbitrary point, I have essentially shown that any point in R3 has a pre-map under L. So how do I show that? So the way to show that is take any y3, let y is equals to y1, y2, y3. Okay. Now for y equals to y1, y2, y3, can you represent it in f1, f2, f3 terms? Obviously you can. So this is equals to some g1 times f1 plus g2 times f2 plus, or let's call it lambda 1 times f1 plus lambda 2 times f2 plus lambda 3 times f3. Now since f1, f2 and f3 are linearly independent, lambda 1, lambda 2, lambda 3 are unique. So for any point there will be a unique way to represent it in terms of f1, f2 and f3. Okay, now once you have represented this lambda 1, lambda 2 and lambda 3, okay, so there will be a unique lambda 1, lambda 2, lambda 3. Then we can say then the x that you are looking for is nothing but lambda 1, lambda 2, lambda 3. Right? And this happens because you see, when you put it under L times x, it's going to be nothing but lambda 1 times f1 plus lambda 2 times f2 plus lambda 3 times f3, which is going to be equal to y1, y2, y3. Okay. So this is how you can do the second.